Hi everyone, my name is Yishuan. My team Linsha and I have built a large-scale fraud detection system this semester. More specifically, we've used the latest design principles like cloud computing and microservices to make the project more scalable and secure. We've finished all components of the project and are eager to share the results with you. So the objectives, since this class is called Big Data Analytics, we want to incorporate features from both fields, big data and analytics. When it comes to big data, the first and foremost feature should be scalability and reliability. It has been the foundation of the core system design since day one. So we really want our system to handle large amount of traffic while having the ability to handle even peak volume traffic. So for example, that is 10 times higher than average. We also want our system to be highly available. So that means minimal downtime. The system is always available. Real-time correction. The second feature is unique to fraud detection. We need the system to be responsive to user input. In other words, if the system is wrong, the user can correct it. It poses a unique challenge to machine learning modeling because parametric model cannot respond that quickly to user changes because it has to wait for another training period. Finally, high classification accuracy. We want our model to both have high precision and recall, but among these two important metrics, we want to prioritize low false negative, aka high recall. We should not let fraudulent transactions get away. While maintaining a good recall score, we also want to reduce false positive as much as possible. That meaning improve the precision without sacrificing too much of recall. Challenges. As a project designed to work with large volume of traffic, it must tackle the infamous 3V challenges posed by big data, volume, velocity, and variety. Volume in our project means high requests per second with potentially much higher peak volume. So how can our system dynamically scale up and down according to the traffic? Velocity. Velocity has two meanings in our project. First, the users expect the classification result to be returned by our system in a few seconds. So how can we achieve that when the traffic is high? For users, velocity also means that having the option to correct classification result and retry without waiting too long. So if we use parametric models, that means the user have to wait after correction for the next training step. All right, so variety. Variety has a different connotation in our project. Variety does not mean, the difference in data sources like CSV files, text files. It means that as time changes, even data from the same user shifts in its distribution. So for example, somebody lives in Los Angeles and then moves to New York, his or her data changes the distribution. Okay, system design. So here's the overall architecture of the system. So we have three components: online service, nearline service, and offline service. So for the online service, whenever a user submits a transaction to the API, it gets routed to a corresponding handler. For example, for classification, it's going to go to a temp endpoint, and then the data is pushed to Kafka. We use Kafka here because we want the data to be buffered, and we want to make sure all transactions are consumed. And if the backend system is down, the data will be stored in Kafka for a short amount of time. All right. So once the classification result is ready, it's going to be cached to Redis, and then checked by another endpoint, API endpoint called correct. So instead of having a WebSocket between the user and our API, we have two HTTP requests, one attempt and one for checking result. We do that because we want to minimize the cost of maintaining the connections, because maintaining WebSocket connection is very expensive. All right, so the nearline service approves approved transactions on Kafka and batch write it to DynamoDB. By doing so, we improve the throughput of the database and preventing it from becoming a bottleneck. And finally, the offline service. Privacy protection is important, especially when it comes to credit card data. We want to downsample the database and only keep a small portion of data for model training. So even if a data leak happens, the impact will be minimized because the data in the database is downsampled by our offline service. So system design. So here's the 3 points that our system address: the volume. So we address the problem of large volume by using highly scalable microservices. So for example, API Gateway acts as a load balancer. It supports very high request volume. Kafka for queuing. We have different numerous numbers of consumers and publishers connected to Kafka, and the system will not crash at peak volumes. We also use microservice-based code. That means the system can automatically scale up and down according to the traffic velocity. We use Redis for result caching rather than using database. And by doing that, we make our results more readily available for users. And we also choose an unsupervised model that's fast and variety. We use Spark to constantly sample database to keep only the latest data in the database. By doing that, our machine learning model can easily adapt to the shift in data distribution. We use unsupervised models so that the latest data is always taken into consideration because, every time an invocation is made, all data is used for classification. Okay, so much for system design. Let's shift the focus to machine learning algorithm development. So as I mentioned, parametric model is not suitable for our applications since users cannot change the classification result between 2 retraining steps. So we decided to go with unsupervised models. After some preliminary research, we have identified 3 promising machine learning models that are isolation forest, local outlier factor, and one-class SVM. So we choose this. The next step would be evaluating the velocity and accuracy of the 3 models. So this graph shows the runtime of 3 different models. As you can see, the blue one, isolation forest, takes a lot of time when it comes to inference, and one-class SVM is much faster. However, if you take a look at the precision and recall score, SVM does not have a very good precision, but it does have a very high recall. I would say that local outlier factor and isolation forest are relatively on par with each other. But however, neither model has a very good performance. So I'll talk a little bit more about how we improve the performance in the next slide. So we first try to improve the performance by doing feature engineering. We actually tried to use an autoencoder for this job, but as it turned out, autoencoder does not improve the performance by a large margin. It's because that the autoencoder changes the distribution of data since all 3 models are trying to model the distribution of outliers to differentiate the distribution of outlier from the inliers. Okay. So after giving up autoencoders, we decided to go with the basic feature engineering approach. We address the geo coordinates. We calculate distances between 2 coordinates between your home and shopping address. And we believe that's semantically meaningful. We also encoded shopping types, for example, groceries or petrol, and provide transaction time so that it offers more semantics into a transaction. So after using feature engineering, we significantly improved the performance of our models. So go back to the previous slide. As you can see, the highest precision is around 0.5, and the highest precision recall is around 0.7 for isolation forest and local outlier factor. But with the new features, we were able to achieve 0.7 precision and recall. Okay, so the next step we did is using a cascading classification pipeline. Because SVM offers very high recall and it's fast, we can use it for preliminary filtering. So it filters out legitimate transactions and only pass a suspicious transaction to more powerful models like a local outlier factor or isolation forest. So in this case, we stick with local outlier factor. So the red dots are the performance of a pipeline model. And as you can see, it's much better. It's better than local outlier factor and isolation for it individually. Okay, so let's switch to a live demo.
Okay, thanks, Zishan, and thanks for the introduction. So this is Ling Xiao, and I'm very excited to do the live demo for our groups. So first, show our work. So as you can see, as also Zishan talked about, we host all of our services in the cloud for scalability and reliability concern. As we said, we host our machine learning model, which is the isolation tree in SageMaker, which supports interactive query in a scalable way. So we also configured it to scale in different availability zones to ensure its availability in case of system down. We persist our data in DynamoDB, which is also highly available and scalable. We use message system in Kafka hosted in the MSK. And we use Lambdas and API gateway to bridge several components and make them glued together. We also host our Spark in EMR to downsample the data to keep it minimal. And we host our front end in the S3, which is shown here. So first, we like to show the interactive use case of our system. So due to time constraint, I will use the two pre-uploaded data. So first, I click the genuine data button, which will populate the genuine data in one of our records. And I submit the record, and it says your transaction is received. And then typically, a post machine will check your user ID and transaction ID and to see if the transaction is approved. And I click check, and we can see that this transaction is approved. Refresh. So now let's take a look at the fraud detection. And I click the fraud button, and the fraud transaction is populated. This transaction has a very deviated pattern than the normal transaction that we pre-uploaded. And we populate the user ID and transaction ID for the fraud data, and we hit check. And unfortunately, this transaction is not approved. So as we also talked about in the previous presentation, we have our user verification where user will receive a message to correct potential fraud if it is actually not a fraud. We temporarily, we will not show that in this demo because of the time constraint. And as we shown in previous demo, so when a transaction is flagged as fraud, and user will receive a safety link provided by us to correct it if they think it's not the fraud. So after this transaction will be flagged as a normal transaction. And in the later on, we will also collect this kind of pattern as the normal pattern of the user. I'll go back to our demo. And as we can see, we need to have a better way to visualize how our machine learning model performs. So we also created a visualization test. So we can upload a medium-sized records, which have already feature engineered, and which has about 70 to 80 records of transactions. And we hit start test. And these transactions are uploaded one by one, separated by 0.1 seconds as we configured. And as we can see in this graph, sorry about like the shaking graph because we are not front-end guys, so this is just for display purpose. So there will be 4 bars. The left 2 bars are for normal transaction, and the right 2 bars are for the fraud transaction. So the green bars means correctly classified, and the red bar means wrongly classified. So the leftmost green bar means the normal transaction is actually classified as a normal transaction, and the left red bar means a normal transaction that is misclassified as a fraud transaction. And as we talked about, we can send a correction message to user, and the user can correct it due to their preference. And the right green bar means the fraud transaction that is actually flagged as fraud by our system, and the red green bar, and the right red bar means the fraud transaction that we are unable to classify it as a fraud. So as we can also check the console here, And we have a total of 62 normal transactions, and we have 15 fraud transactions, and we classify 61 out of 62 normal transactions, and we classify successfully 12 transactions out of 15 fraud transactions. So the precision and recall are pretty high for this data set. So the precision is about 12 over 13, and the recall is about 12 over 15. So yeah, so this is a short demo of our app. So go back to our presentation. And our app is of very high business value. First is an off-the-shelf scalable fraud detection system that follows popular microservices and big data principles, which is of huge industrial importance. And second, we provide an upgradable platform that runs any machine learning job on streaming data. So as we talked about, we host the model in the SageMaker, and we can retrain and redeploy the model as we want. And we can also transplant this endpoint to Internet of Things devices, and we can also use it for spam detection, etc. And also we use CloudFormation template, so the project is also portable. So we can deploy the whole project with just a simple click. And also, fraud detection is always a heated topic, and also a challenging topic as well in the industry. A lot of unicorns are very famous for transaction fraud detection, like Stripe. And also, we are successful in connecting several components together as a whole ecosystem. And yeah, we fulfill our promise for this project. And this is the end of the demo. And thank you very much.